factor 0.866 is a conversion factor used in three-phase electrical systems to relate line-to-line voltage to line-to-neutral voltage. In a three-phase system, there are three phases, and the voltage between any two phases is called the line-to-line voltage, abbreviated as volts line-to-line. The voltage between any one phase and the neutral point is called the line-to-neutral voltage, or volts line-to-neutral. These two voltages are related by a factor of the square root of 3, which is approximately 1.732. The number 0.866 is the reciprocal of the square root of 3, or 1 divided by 1.732. This value is essential for converting between line-to-line and line-to-neutral voltages. The relationship between volts line-to-line and volts line-to-neutral is defined by the equations volts line-to-neutral equals volts line-to-line divided by the square root of 3, and volts line-to-line equals volts line-to-neutral multiplied by the square root of 3. This means that volts line-to-neutral is always less than volts line-to-line. The 0.866 factor is used when you know the volts line-to-line and need to find the volts line-to-neutral. You multiply the volts line-to-line by 0.866. Conversely, if you know the volts line-to-neutral and need to find the volts line-to-line, you would divide the volts line-to-neutral by 0.866, which is the same as multiplying by the square root of 3. Now let's look at the voltage drop calculation and how this factor applies. The voltage drop formula you mentioned, volts drop equals 2 times K times L times I times 0.866 divided by Cm, is specifically designed for three-phase circuits when you're working with line-to-line voltages and want to find the voltage drop per phase. In this formula, firstly, volts drop represents the voltage drop in volts along the conductor. Secondly, K is the conductor constant, representing the direct current resistance of the conductor material per unit length and area. Its value depends on the material, typically copper or aluminum, and the temperature. Thirdly, L is the one-way length of the conductor in feet. It's crucial to use the one-way length because the current flows from the source to the load and back. Fourthly, I is the current in amps flowing through the conductor. This is the load current that the conductor is carrying. Fifthly, Cm stands for circular mils, which is a unit of area used to express the cross-sectional area of a conductor. It is calculated by squaring the diameter of the conductor in mils, where 1 mil equals 0.1 inches. The factor 0.866 is included in this formula because the voltage drop calculation often involves using the line-to-line voltage, but the formula needs to account for the line-to-neutral voltage to accurately determine the voltage drop per phase. By multiplying by 0.866, you are effectively converting the line-to-line voltage to the line-to-neutral voltage, which is necessary for the calculation. Without the 0.866 factor, the voltage drop calculation would be inaccurate for a three-phase system using line-to-line voltage. The constant 2 in the formula accounts for the fact that there are two conductors in the circuit, one for each direction of current flow. To better understand the application, consider an example. Suppose you have a three-phase circuit with a line-to-line voltage of 480 volts, a conductor length of 100 feet, a current of 45 amps, a conductor size of number 6 American wire gauge, which has a circular mil area of 26,240, and a conductor constant K of 12.6 for copper. Using the formula volts drop equals 2 times K times L times I times 0.866 divided by Cm, we can calculate the voltage drop. Plugging in the values, we get volts drop equals 2 times 12.6 times 100 times 45 times 0.866 divided by 26,240. This simplifies to volts drop equals 98,290.8 divided by 26,240, which results in a voltage drop of approximately 3.75 volts. This voltage drop represents the drop in voltage along one conductor of the three-phase system. It's important to ensure that the voltage drop remains within acceptable limits, typically 3% for branch circuits and 5% for feeders, to maintain proper operation of the connected equipment. If the voltage drop is too high, it can cause equipment to malfunction or operate inefficiently. To reduce voltage drop, you can increase the conductor size, shorten the conductor length, reduce the current, or increase the supply voltage. Understanding the 0.866 factor and its role in three-phase voltage drop calculations is crucial for electrical engineers and technicians to design and maintain efficient and reliable electrical systems. Always refer to the National Electrical Code, also known as NEC, and other relevant standards for specific requirements and guidelines related to voltage drop calculations and conductor sizing. Remember that this explanation is a general overview, and specific applications may require more detailed analysis and consideration of other factors such as conductor temperature, installation methods, and harmonic distortion. Always consult with qualified professionals and follow all applicable safety regulations when working with electrical systems. In summary, the 0.866 factor is a key component in three-phase voltage drop calculations, allowing for accurate conversion between line-to-line and line-to-neutral voltages. By understanding its significance and applying it correctly, you can ensure the proper design and operation of three-phase electrical systems. Always double-check your work and consult relevant electrical codes and standards. The voltage drop calculation is volts drop equals 2 times K times L times I multiplied by 0.866 and divided by Cm. This formula is crucial for understanding the effects of voltage drop in alternating current three-phase systems. The derivation of 0.866 comes from the relationship between line-to-line and line-to-neutral voltages in a balanced three-phase system. The line-to-line voltage, often denoted as volts line-to-line, is the voltage measured between any two of the three phases. The line-to-neutral voltage, volts line-to-neutral, is the voltage measured between any phase and the neutral point. In a balanced three-phase system, these voltages are related by the formula volts line to line equals the square root of 3 multiplied by volts line to neutral. Conversely, volts line to neutral equals volts line to line divided by the square root of 3. The numerical value of the square root of 3 is approximately 1.732. Therefore, 1 divided by the square root of 3, or 1 divided by 1.732, is approximately 0.577. However, the factor used in many voltage drop calculations is 0.866, which is not exactly 1 divided by the square root of 3. The reason for this discrepancy is that the voltage drop calculation often includes another factor to account for the power factor of the load. The power factor is a measure of how effectively the electrical power is being used. It is defined as the cosine of the angle between the voltage and current waveforms. In a purely resistive circuit, the voltage and current are in phase, and the power factor is 1. In a reactive circuit, such as one with inductors or capacitors, the voltage and current are out of phase, and the power factor is less than 1. When the power factor is less than 1, the current is higher than it would be in a purely resistive circuit for the same amount of power. This high current causes a greater voltage drop in the conductors. To account for the power factor, the voltage drop calculation is modified to include a factor of cos theta, where theta is the angle between the voltage and current waveforms. The factor cos theta is equal to the power factor. When the power factor is 0.866, the angle theta is 30 degrees. This means that the current is lagging the voltage by 30 degrees. In this case, the voltage drop calculation is multiplied by 0.866 to account for the power factor. The complete voltage drop calculation is volts drop equals 2 times K times L times I divided by Cm multiplied by 0.866 multiplied by cos theta. When the power factor is 1, cos theta is also 1, and the voltage drop calculation simplifies to volts drop equals 2 times K times L times I divided by Cm multiplied by 0.866. This is the formula that is commonly used for voltage drop calculations in three-phase systems. It is important to note that the voltage drop calculation is an approximation. It assumes that the conductors are perfectly uniform and that the current is evenly distributed. In reality, these assumptions may not be valid, and the actual voltage drop may be different from the calculated voltage drop. However, The voltage drop calculation is a useful tool for estimating the voltage drop and for ensuring that the voltage drop is within acceptable limits. The acceptable voltage drop limits are typically specified in the National Electrical Code (NEC). The NEC specifies that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual loads, such as lights and appliances. Feeders are the circuits that supply power to branch circuits. If the voltage drop exceeds these limits, it may be necessary to increase the size of the conductors or to reduce the length of the circuit. In addition to the voltage drop calculation, there are other factors that should be considered when designing an electrical system. These factors include the ampacity of the conductors, the short-circuit current rating of the equipment, and the grounding requirements. The ampacity of a conductor is the maximum current that the conductor can carry without overheating. The short-circuit current rating of equipment is the maximum current that the equipment can withstand without being damaged. The grounding requirements are the requirements for connecting the electrical system to the earth. By considering all of these factors, it is possible to design an electrical system that is safe and reliable. Also, keep in mind that the constant K in the voltage drop formula can vary based on the material and temperature. For copper, K is often taken as 12.9 ohms circular mils per foot at 75 degrees Celsius, or 12.6 ohms circular mils per foot at lower temperatures. For aluminum, it is around 21.2 ohms circular mils per foot at 75 degrees Celsius. The formula volts drop equals 2 times K times L times I, multiplied by 0.866 and divided by Cm provides a practical way to estimate voltage drop. The 0.866 factor arises because of the phase relationships in a three-phase system. In summary, the 0.866 is a phase shift value in a three-phase system to relate line-to-line voltage to line-to-neutral voltage.